Welcome all to this lecture. So, in the last class we basically discussed analysis filters and we concluded that we can take a full band signal, we can decompose that through an analysis bank comprising of analysis filters, and then we pass this through the synthesis bank and hopefully we get the reconstructed signal. Now there are a lot of details here when we have to delve into specifics as to how we can build these analysis filters, synthesis filters, etc., and that would be the study during our course of the module on multi-rate signal processing. Okay. So, first let us start with the discrete Fourier transform and analyze this as a simplest filter bank. The DFT matrix is an n by n matrix such that this matrix given by Wn, n for the length of the DFT that you are interested in computing, is given by omega n power k times m. I can put as such that equal to, indicating that this is a matrix comprising of entries which are omega n power k times m, where omega n, and I would say this is a capital W, and omega n is e power the small omega n, which is e power minus j 2 pi upon n. Now the time domain samples can be transformed into the frequency domain using the discrete Fourier transform, and I will recall the discrete Fourier transform. X of k is basically summation m equals 0 to n minus 1 x of m omega n power km. This is a small omega, right. This is a small omega power km, and this is a capital, this is a matrix which is comprising of these elements which are small omega n power km. Now we have the inverse Fourier transform, which is linking the time domain samples and the frequency domain in an inverse way. Given the frequency domain samples, we can get back to the time domain, and that is given by this equation 1 upon n k equals 0 to n minus 1 x of k omega n power minus k times m. So, this is basically our DFT, this is our inverse discrete Fourier transform. And if you think about this matrix, the entry in the kth row and mth column is basically e power minus j 2 pi k times m upon n. So, we can think about this as a matrix multiplication, right. I mean, if you stack all these points, if you take an n point DFT x0, x1, x2 so on till x of capital n minus 1, and then on and then you have these time domain samples small x of 0, x of 1 so on till x of n minus 1, you can think it as a sort of a matrix multiplication, where you are taking the time domain samples multiplying with this matrix comprising of these entries, and then you have these frequency domain samples which are x of k. Now X is W times X. I will just ignore this subscript. Okay, so you can link the time domain samples here. These are time domain samples. These are frequency domain samples, and this is our DFT matrix. Okay, so this is our DFT matrix. We link the time domain and the frequency domain samples. Let us see with a simple example how this is and if our intuition makes sense. Right, if we take n equals 2, then W2, this matrix, is e power minus j 2 pi upon n is 2 here. This is km is 0 0 here. This is e power minus j 2 pi upon 2. This is a constant factor, 0 times 1. This is e power minus j 2 pi upon 2. This is 1 times 0. This is e power minus j 2 pi upon 2. 1 times 1. And if you just simplify this, you get 1 1 1 minus 1. This is e power minus j pi, which is cos pi minus j sin pi, which is minus 1, and the rest happen to be 1 because this evaluates to 0. Now, well, this matrix is for what it is, but if you take a slightly closer look at this matrix, observe this row and observe this row, right. We are just taking a 2-point DFT here, and if you observe the 2 rows of this matrix, 1 1 is basically like the coefficients of your low pass filter, right. If you take the impulse response 1 1, 1 comma 1 basically translates to 1 plus z power minus 1, which is a low pass filter, and 1 comma minus 1 is basically like a high pass filter, right. It is 1 minus z power minus 1. You can just plot the spectrum of this really quickly, and then you can conclude that this is low pass and this is high pass. Now, this sort of gives us an indication that the DFT is doing already something for us in terms of filtering, right. If you look at the rows of the DFT matrix, you are going all the way from low pass filters to high pass filters, and you can do this example for W3, W4, so on and so forth, and you can conclude. Now, this simple example here gives us an indication that from the definition of this matrix W, we can interpret DFT as a filter bank. So now we will go a little further into the analysis. Basically what we do is we consider the sequence x of n, and we basically think about passing this sequence through a delay line which forms subsequences, and then we just look into the aspect of filtering these subsequences through some filter, and then we will try to link all these variables together and see how we can interpret the discrete Fourier transform as a filter bank. So let us start with this basic idea. So consider the sequence x of n from which we generate m sequences Si of n, I equals 0 1 dot 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 till m minus 1 by passing x of n through a delay line such that Si of n is x of n minus I for all values of I going from 0 to m minus 1. Right, this is our setup. So what we do is as follows: we have x of n, no delay is S naught of n, and we have 1 unit delay here. This is S1 of n, so on. Sm minus 1 of n, and we do slightly something different here. Instead of passing through the normal discrete Fourier transform, we will filter it through the IDFT, which is W conjugate, and we get x naught of n, x1 of n, so on till x m minus 1 of n. Right? This is sort of like your subband signals. Now it is pretty straightforward for us to link xk with these SIs. Xk of n is basically sum I equals 0 to m minus 1 Si of n Wm power minus ki, and note this factor minus because it is the conjugate, W conjugate, therefore this is what you have. So basically we are linking a signal here with the input signals that we have before this filter bank. Okay. So the difference is W conjugate is what we have. This is like the IDFT except with a factor of 1 over m. Right. So this is like the IDFT, inverse discrete Fourier transform, without a scale factor of 1 upon m. Okay. So this is our setup. Now we will dig slightly carefully. Now what we do is basically take the Z transform on both sides of this equation, and then we will try to link the variables together. So taking Z transforms, xk of Z equals summation I equals 0 to m minus 1 Si of Z Wm power minus k times I. But the sequences SIs are basically delay sequences, right, and we can link them to the Z transform of x via a delay element as follows. So therefore we can say xk of Z equals summation I equals 0 to m minus 1. So just plug this one here. So it is Z power minus I Wm power minus k times I times x of Z, right, and we simplify this to Z times omega m power k to the power minus I times x of Z. Now we can say x suffix k of Z can be written in the form hk of Z times x of Z, where hk of Z is h naught of Z omega m power k, and h naught of Z is defined to be this filter 1 plus Z power minus 1 plus Z power minus 2 dot 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 plus Z power minus m minus 1. I think this is sort of pretty straightforward for us to visualize. I mean, what we did is this x of Z is basically a constant. We just pull this out, we just have summation because there is no index I here, right. So we can pull this out, and this summation of m copies of Z omega m power k power minus I, we interpret that summation as basically Z being replaced, Z in this sum 1 plus Z power minus 1 plus Z power minus 2 so on, replaced by Z omega m power k. That is what is happening here. And why we need to bring this H naught? This is like our base filter or our mother filter or our low pass filter here, right. We got our intuition with a 2 by 2 matrix. We started off with a 1 plus Z power minus 1, and if we extend this for an m point, we get Z power minus 1, Z power minus 2 so on and so forth. So we have this as our mother filter. This is basically the mother filter, and rest of the filters can be obtained by changing the parameters of the mother filter, because it is being modulated by omega m power k. By having a modulation term, this is basically modulation term. So by having a modulation term, we can construct a modulation factor, we can construct rest of the filters from the mother filter. So what this shows is the following. The DFT system is like a filter bank with analysis filters HK of Z, right. This is my analysis filter, and I stack all these analysis filters and I get my analysis bank. So with this I give you a simple exercise here. Which is for your homework. Obtain the magnitude frequency response of HK of Z, plot them. So basically you will have to verify that magnitude of H naught of Z is mod sine m omega upon 2 divided by sine omega upon 2, and HK of Ej omega is basically you have frequency translates which are uniform shifts of 2 pi k upon m for each of the values of k. So basically verify that magnitude of H naught of Z is given by this, and then use 1 and 2 to sketch the frequency responses. So this sort of gives you an idea how the frequency responses look, and if these filters are overlapping or non-overlapping, and some of these details, right. And this gives you an idea where how these filters are evolving with the modulation of omega m power k factor. Okay. So this is the simplest filter bank. So before we get on to the next topic, we have to basically understand a sort of summary of the time domain descriptions of multi-rate filters. Now y of n equals summation k equals minus infinity to plus infinity x of k h of n m minus k, and this is the response if it is an m fold decimator n minus kl if it is an L fold expander, I would say interpolator, and this is of this form x of k times h of n times m minus k times L if it is an m upon L fold decimator. And whichever is convenient to you, if you were to go in the time domain or in the frequency domain, you can feel free to adopt whichever path you would like to choose. That makes it easier for you to understand and interpret the flow of the signal through multirate operations along with filters. Okay. I think what we have to interpret here in these multirate operations is, I mean, we have filters along with it, right. We filter followed by downsampling, or we upsample, and then we follow this with a filtering operation, or we do an m by L decimation post filtering. So these are sort of filtering operations that we do, and one has to interpret this this h of n as the impulse response of that filter that governs multirate operations that either precede or follow the sampling rate conversion operations, as the case might be.